not quite sure I'll really get to polyfold definitions, but I will give you sort of a wish list for the general form of well, what polyfolds should do. And I think that's, in particular for polyfolds, that's crucial, because once you know what you want to do, the things that you do actually are quite natural. So, and that opportunity will also lead to yet a few more details on the proof of Arnold. So, what is our general form, and what kind of properties would we like for our, black box machinery that we stick a moduli space in and get, numbers or a proof out? So, first thing, right, we would like it to be compact. Somewhere deep in the theory you would need it Hausdorff, and most likely you want it metrizable. So, I'll just start with that. And I've tried to argue that really all descriptions that are reasonable are in terms of some zero set of a section, except there's some transition maps going on, and so it's best to think of this as a quotient, namely the realization when you have two categories, no two categories here. So a base and a bundle category, really. And let me try to be a little bit more formal about that. So what do I mean by E being a bundle over B? Well, there better be a functor from E to B. And I would like E to sort of be a vector bundle. So now when I say B in B, I probably just mean objects. And then this is a subset of the object space of E, and I would like this to have a vector space structure. Well, and then, there will be morphisms between different B's, and you would like the morphisms to somehow be compatible with the vector space structure. Which then allows us to talk about the zeros in those vector spaces. So that really becomes another functor. And there will be yet another section. So 0 now goes from the base to E and gives you the, in terms of objects, just the 0 in every fiber. And now that we have 0, we can write down our other section, sigma, which should also be a functor that way. And they are sections in the sense that when I compose them with first the section, then pi. Both of these should be the identity functor on B. So that also ensures that pi is a surjection. Right, and now it makes sense to talk about, sigma inverse of 0. It's the sort of the place in B where the two sections have the same value, which is then a subset of the objects, and this is, as usual, that subset modulo the equivalence relation generated by the morphisms in B.
What does the vector space structure look like for pi?
In general or in practice?
I don't.
I mean, in general, that's it, right? It's a set. It has a vector
You
space
only
structure,
consider the
meaning there's a
objects.
sub on the objects. Yes. Yeah.
So you consider the set of objects.
Right.
For them
Yes.
to be.
Yeah. So on objects, and you would probably would like it to be compatible with morphisms. So that means the morphisms, when you know, on between different fibers here, should be given by linear maps. And I should probably, well, vector space means, you know, probably over R. No funky rings here. All right. So one common misconception somehow is that just a compact set might have sort of a canonical description of, you know, in terms of such a section. But really, that makes no sense. I can write like the point, you know, as zero set of a, you know, index 0 problem or an index 25 problem or an index minus 25 problem. You know, either transverse or non-transverse weight. One direction probably doesn't make sense. You can make it. I can write the point as index minus 25. At least. Well. Anyways. So at least the index somehow needs to come from something more than just that compact set. You know, and in our cases, we usually have some Fredholm index of a, you know, d bar operator. We expect that to be the virtual dimension of M bar. So, and in fact, we have these local Fredholm descriptions pretty much everywhere. Which that's what I would sort of call the moduli problem. Really, somehow this modular space isn't just a compact set. It's cut out by some PDE, by something, from some better behaved ambient spaces. And so that somehow should induce sigma. And in fact, it should sort of induce sigma uniquely up to some notion of cobordism of these things. Otherwise, there's no hope of, you know, extracting, say, Gromov-Witten invariance from a situation like this. But let's not talk about uniqueness yet. So what I just want to say here is that sigma on the level of objects should be induced by the local Fredholm descriptions. So, well, remember our Fredholm descriptions. Unfortunately, I think I was using the same kind of letters. So let me write a little bit of a sort of local piece of bundle sitting over some open set in a Banach manifold, right? And usually it was kind of just a d bar operator, right? That would cut out a piece of a moduli space, so U would be like a local slice to the reparameterization action. And so if you then look at the holomorphic curves in that local slice, there's a homeomorphism to an open set in my moduli space. That would be really nice. In general, there's a finite isotropy group acting on this whole thing, which, you know, in this case is going to become part of the morphisms of my category. And then I should, quotient out here by the morphism, so I'm allowed to quotient by gamma for this embedding. So the local Fredholm descriptions, if you have a cover by your a cover of your moduli space by local Fredholm descriptions, you pretty much have a pretty good idea of what these categories should be. They should be the unions of all the bases and the unions of all the bits of fibers, and your section simply should be the d-bar operator everywhere. And then you have two types of morphisms. One comes from the isotropy, and the other comes from overlaps between these. And that's, discussed that before. The overlaps are a little complicated because really you only have good overlaps in the moduli space. Because these U's might be local slices that don't intersect at all, in some map space of maps. So they only intersect in a space of maps. Modular reparametrization, which doesn't have a differentiable structure, and so then you have issues with what are the transitions. So on the level of objects, it's pretty clear what this should be, and so really the problem lies in what the morphisms are supposed to be. Right. And this also might not make a whole lot of sense to you if you're thinking about the case of the Kuronishi structures. So really there's some extra stuff you have to do once you have a Fredholm description. You might have to stabilize, and you might have to take finite dimensional reductions. In the level of Fredholm descriptions, it's good to say, if d bar is a Fredholm operator here, then its index will be locally constant, and you'd like that index to be preserved by transition maps, certainly. So preserved, I guess, or compatible with morphisms. So see how this sort of, so you do want a little bit of sort of Fredholm property of your section and also a Fredholm index of your section. And let's see how that arises maybe in the cases that we've vaguely looked at. So, of course, cheating here massively at all times. So, right. So Siebert, right, said, well, a section is really only C1 in all but finitely many directions, and so I don't want to be really precise about this. But he has this sort of extra notion of what it means to be Fredholm, namely that it has something that he called Kuronishi structure, and that I like to call global stabilization, which in this general form is a bundle that sits over the same base and doesn't even need to inject, it just needs to have a morphism, bundle morphism, in this case a functor, to the bundle over, the bundle with infinite dimensional fibers. And this should be so that, the fibers, let me write F sub B for a fiber, those should all be finite dimensional. And the image of them should cover the co-kernels. And in this case, here, so I'm not going to try. So it should cover the co-kernel of however many derivatives of my section are actually defined. And once you have that, you can talk about the index in different ways. You could talk about it as you can talk about it as the index of this differential, however many sections, however much of it is defined, but then you have to add those finite dimensions, plus sort of the non-differentiable dimensions. But that ends up to be the same thing as, right, so what he then did is he took sort of combined the zero set within F. And that became sort of finite dimensional manifold. So if I take a point in this bundle and a neighborhood in, let's see, I want to map B by the section into here and pull it back with iota, I think. So this should all be thought of on the level of objects. This minus the dimension of the fiber of F that contains F. This allows for iota to not be injective at all. So what you should think of here is, let's see, if iota is injective and hits exactly the co-kernel, then this is the co-kernel. And this neighborhood here, you want to think of this as essentially the B's in B, for which sigma of B is in iota of F. So the perturbed holomorphic maps that are perturbed up to this F, up to this stabilization. There's just this whole peskiness of iota possibly not being injective, and so you try to pull it all back into your bundle F. Yes.
So sigma as a functor send each open subset of B to open subset of E.
No, it's not an open subset. Yeah.
Each object is an open subset.
No, each object, sorry, objects here are points. I didn't say that at all. Well, I mean, right, so, right. So when I have a finite dimensional, when I have a Fredholm description like this, I'm not making U an object of B, I'm making U an open subset of the object space of B. Does that make sense? So objects will be some kind of disjoint union of UIs. Right, and then the E's will be, well, maybe in fact, so let's say we don't even need non-trivial bundles, we could take trivial bundles. Let me take a straight E for a moment here. So then the object space will be the disjoint union of UI times EI. And my section is strictly, it's just, a map from UI to EI. So it's its image will be the graph in here. And so.
Yeah, but how can I tell that from the category now? From the category now.
You can't. This is a general description of, this general description doesn't know everything about how I've constructed it, right? This is just sort of trying to tell you how you should think about it. But generally, right, so sigma is a section, so in terms of objects, this gives me a subset of the object space of E, and then I can just look at the preimages in the object space of F. So when I write categories and they look like they ought to be sets, I think what I mean is the object space. So the reason I did the second sort of description of the index is that already sort of tells us that there's a nice somehow transition from, if you have a Siebert type description of your moduli space, you do get, I believe, a Kuranishi description, in fact, with one chart. Right? Because that's exactly what he did, right? He used this description to somehow get a global finite dimensional reduction, where really your moduli space then is a zero set of a section in over a finite dimensional manifold. And that's what our Kuranishi charts are supposed to be. More general, I guess, if you have some kind of description like this, and maybe not quite a global stabilization, but you have these stabilizations in every little, maybe connected component of the object space, you can make your finite dimensional stabilizations. So there's not much of a Fredholm problem in the Kuranishi world, simply because everything is finite dimensional. So I can just say how it comes from something on the left side. So see, you can call this with twiddles here. So then secretly that ambient problem sits here, and F, actually I'm not going to call that a twiddle, because that's sort of F in this world kind of is my bundle then, which also has a map. So F actually is part of the Kuranishi section, except, well, F restricted to something, namely F restricted to, well, really this thing, which doesn't quite sit in there. So, but this is my, B twiddle. This is my base, B. And then the section, but this, so this now sits inside my F. And so the section here simply becomes the identity on F. So that's how you sort of, from a stabilization, get Kuranishi charts. And really secretly what you want to think here is that you've just looked at solutions that are not holomorphic curves, but not the preimage of 0, but the preimage of stuff in F. Right? And then F sits over here, and the section would just be given by sigma twiddle. Right, so this whole sort of extra complication here just comes from F not being mapped injective to E, possibly. So Fredholmness here really means that these two things are finite dimensional. So E object spaces of E and B, and hence the morphism spaces will be finite dimensional. And smooth maps between finite dimensional spaces are very, very Fredholm. And so that means you can now here write the index actually again in two different ways. You could write it as the dimension of the object space of B minus the rank of the fiber. So yeah, let me write this rank of fibers. Which is exactly the same formula as this one, right? Because the fibers are the fibers of F, and this neighborhood and that stuff is my base here. And then general linear algebra tells me that that is in fact equal also to the index of the differential of my finite dimensional section. Because it's compact, it's a compact perturbation of 0, and 0 as a section has kernel exactly the object space and co-kernel the entire file. Proof. Good. So now polyfold world sits somewhat uncharted in between, and what's also a little frustrating is that we don't really have a proper sort of a nice generalization of the notion of Fredholm section in a Banach bundle on the board yet. Right? This is a finite dimensional reduction, and this just says, well, it's Fredholm if you can add something finite dimensional to make it transverse. So in polyfold world, and this here should follow from a definition of Fredholmness. So that should just be a result, and that's what happens in polyfold world. So here, when I look at my section on object level, it's smooth in some appropriate sense, and so the definition of it being nonlinear Fredholm has two parts. There's a nonlinear part which formalizes elliptic regularity into some notion of regularizing. Regularizing. So that's something you need and extra, but mainly there is a notion of differential now, and there is a notion of linear Fredholm, and we'd like that to be in fact Fredholm at all zeros. So now there is a story here of how these things should imply each other. So once you have this, you should get at least local stabilizations. There's a bit of an interesting question of when you can get global stabilizations. I think when isotropy is trivial, you can get global stabilizations. And when isotropy is non-trivial, there's some condition on having locally sort of stabilizing things that are invariant under the isotropy. So, right, and if anybody looks at Joyce's work on D-manifolds, he in the orbifold case, he has an interesting extra condition that looks very much like asking there to be not just local stabilizations, but global ones. But the thing is, once you have a global stabilization, you have a global reduction. So you have a Kuranishi atlas with one chart. So I think that's probably not the most interesting case. So for me, I like this better because it's a more general condition. It gives us local stabilizations, and then local stabilizations give us finite dimensional reductions. There's a grad student of Hofer's, Dingyu Yang, who sort of formalized that, and who also, from Kuranishi structures, made a construction of polyfolds. And, well, the analyst's, or at least my personal analyst's taste is that this is the natural direction, and going back is a little sort of ad hoc. But it's nice to know that the two theories should in essence be equivalent. If you now do sort of K-theory and try to, classify all Fredholm sections, you should get the same thing. Which is really, I think, that is Joyce's overall goal in this whole game. Right. And what else? Right. These Fredholm operators simply have an index, so here, no discussion. Index simply is the dimension of the kernel minus codimension of the image. Well, really there's massive complication in what I mean by Fredholm. But yeah, that's for later. Sort of the whole project of going from global picture to local picture is kind of a non-standard way of teaching these things, I hope. But well, I think it is non-standard, and I hope it's helpful. So, which also means you can check out at your chosen level of details. Whereas otherwise, if we start at the details, you keep waiting for your chosen level of details. So this is what you should think in the specific abstract settings of what this section looks like, what it means to be Fredholm, and what the index is. And this is really about the general form and not sort of properties of the regularization yet. And it's just where does it come from, and what nice form does this section have? Right. So index, I think, is still down here. So there's exactly that. Locally induced by the Fredholm descriptions. But we would like morphisms to come from someplace. So, right, on the zero set, so the morphisms of B on the zero set are simply determined by the condition that my moduli space here should be, that realization. And if I call this a little embedding here, psi, then this should be induced by all the local psis. So that tells you some of the morphisms, but only on the zero set. And so outside of the zero set, this really is extra data. That's why I call these things transition data and not just transition maps. So me, sort of transition maps are induced by charts, whereas transition data is kind of extra stuff. So this is really extra structure of your description in terms of a section. Extra structure, extra data. So, and again, there was earlier this question that why do you need to glue these things together outside of the zero set? And I think that's a fantastic question. And the fantastic answer is that we're going to perturb sigma to get our solution spaces locally smooth, And so then the perturbed zero set needs to also get glued together somehow. And if we only glued the zero set together, we wouldn't know how to. So that's where we need that extra structure. So once we have that, we can ask ourselves, well, what if we make it locally, transverse and regular? Then our zero set would have exactly the dimension that's given by the Fredholm index, and that's why this is also often called the virtual dimension. And I'd like to insist that it's not just the virtual dimension of the moduli space as a compact set, but really the moduli space together with its section that cuts it out, because that knows what dimension that thing is going to want to have once we've made it smooth. And so, since we're really only going to expect sort of invariance from this pair, of course the question is, how unique is that section? So what kind of equivalence relation could we have between such descriptions? And that's a complicated story. But, well, I think for the Arnold conjecture, we don't actually even need to ever get uniqueness, I think. Let me still say what I think can be done. So there is a general notion that's used for orbifolds of, what is that? Morita equivalence. And that's somehow something like two categories, B and B prime, will somehow be equivalent if you can embed them both in a common one, and the common one also has the right structure. So in our case, that would have to come with the compatibility of the bundles and sections. So here, sigma would be proportional to sigma prime if that. Right, so embeddings here also. And right, so these are both descriptions of the same moduli space. Right, from the zero sets, there's a functor that just takes the quotient and goes to the category. That's just your moduli space with trivial morphisms. So all of these are functors and categories here. And now you'd really like to just sort of write M bar in the middle here, and also take the zero set here and a projection there. And as such, I think that notion of cobordism would not be enough in the world of Kuronishi structures. Simply because when you're taking all these finite dimensional reductions, there are finite dimensional reductions that are just not compatible within the same Kuronishi atlas. So I think in the polyfold world this is probably enough, but in the Kuronishi world we need a little bit more of a trick. So polyfold, I think, can look like this in Kuronishi. We have somehow different choices of obstruction bundles here that are not nicely compatible. We'd like to separate them. And the simple trick of separating this is to ask this Kuronishi section to just not be a Kuronishi section for M, but for M times the interval. And then I'm going to embed this moduli space in here as the copy that sits at 0, and I'm going to embed this one as the copy that sits at 1. And then somehow the idea is that if I have some data from sigma that covers some bit here, and from sigma prime that sits here, and these two by itself don't need to be compatible, so I don't, need a map somehow directly between B prime and B. I would need transition data in this bigger thing, but I just need, a chart that covers the rest here. Into which both B and B prime embed. So that's sort of the separation along 0, 1. That works nicely. Right, and I think the reason why you need to do this extra separation, that sort of again looks like another, well, it's sort of a spaced out version of Morita equivalence, is that you're tying everything together over one single space here. And you're not just asking for somehow homeomorphisms between those 0 sets. And this is probably the last I want to say about this notion of cobordism. It's all in terms of notions that we have there. This is a compact space again, and the 0 set of some Fredholm section. So you can think of these things in exactly the same way. When you try to work these things out in glorious detail, we ended up sweating a lot more, because this notion of moduli space with boundary is kind of a lot more pesky than the notion of moduli space. This is a very nice moduli space with boundary. Well, if M bar has no boundary, then it's really clear what the boundary of this thing should be. And that makes things nice, because then at the boundaries, you have sort of a nice product structure. And so you can lift whatever data you have here to a neighborhood by just taking a product with a small open interval. So in general situations where you think there should be some boundary, that's not going to be as easy, because you're not going to have the boundaries, the product structure, even on the level of your modular space. So warning to the Y is about trying to do these things with boundary. Okay, but so we're hoping that our moduli problem essentially induces to us, this sort of Fredholm section that's unique up to something. And then what should our abstract regularization black box do with that? So here's the same thing again. I would now maybe like to fix an index, or take a connected component of fixed index. And so now, for the umpteenth time, I'm going to write down something that looks like the regularization theorem in finite dimensions, except now it kind of makes sense in terms of functors. I'm going to write this down in the case where my underlying one, right? Here's something else I didn't tell you about these categories, right? The base space somehow should have some kind of smooth structure that allows me to talk about its boundary. So really what you want to think of is union of finite dimensional manifolds, or here Banach manifolds, or later on M polyfolds. They have a notion of boundary, and when the boundary is empty, the story is easier. In the Arnold conjecture proof, we wanted this story for index 0, although the stuff might have boundary. But we don't actually need uniqueness in the Arnold conjecture case. So this is going to hopefully, right? Yeah, this is going to give us the right thing. So I guess what I want to say, this wish list should also apply when there is boundary. Except you might not have uniqueness. So, but, right, so what do we have? We would like a number of section functors now. Of my bundle. Oops. That give me transversality in some appropriate sense. I'm going to fold transversality into this statement here by just saying that whenever I have a section functor in here, right, I have vector space structure, so I can add my two section functors. I can then intersect them on the object level with the zero section. That's again going to give me, well, I'm then taking the full category generated by this, I'm going to take its topological realization. And, so if that was transverse in the appropriate sense, then the implicit function theorem in my abstract world should tell me that the zero set is a, well, manifold, if you're lucky, in terms of isotropic groups of the correct dimension. If you're not quite so lucky and there is isotropy, you need some kind of version of a multi-valued section functor, which is just like multi-valued sections except with appropriate extra morphisms. And then you're not going to get a manifold, but a weighted branch manifold. So again, there's no, right, if this thing was transverse without having to perturb it, then isotropy gives you orbifold singularities. But if it's not transverse, then isotropy usually forces you to go outside of the sections, and you're only going to get transversality with multi-sections, and then you're not going to get an orbifold because of this multi-situation, so then you're going to get these branch manifolds and need to read off the weights from the multi-values. But we believe that there is a well-defined theory of these things. And so this should be true for general, whether I have boundary or not. I should have transverse perturbations. Uniqueness means when I now take another section, transverse section functor in that same set, which might have some other conditions to it, then its associated perturbed zero set should be cobordant to the other one in the appropriate category. And then we have one extra thing that we needed for step 5 of our proof of the Arnold conjecture, which is really, and that's an axiom that every regularization should fulfill. So if my section is already transverse in an appropriate sense, maybe on some open set, then I'd like to be able to perturb by 0 on that open set. Now, I would have to shrink it a little, so, or have transversality a little bigger. I think the cleanest way of saying this is to assume that the realization of the 0 set intersected with U is compact. So, in particular, then this applies, right, if U is a connected component of my base, right, for example, given by specific energy and index, and I have, the connected components will have to be compact if the whole union is compact. So that 0 set will be compact, and then I would like to be able to perturb. So there should be at least some perturbations in P that simply vanish on that set. So, and that's exactly what we need in this last step of the Arnold proof, where, right, you want to see that your I map comes from the identity plus something of positive energy here. Oops. The EIs are all bigger than 0. Right. And go to infinity with I. And we got that in the dream proofs just by saying that, well, if the energy is 0, there are no holomorphic curves, so this is the empty set. And if the energy is 0, the only holomorphic curves that there are here of index 0 are completely constant with the same critical points. So the empty set is certainly cut out transversely. And for those constants, you can just write down the linearized operator by hand and see that they're constants. So sigma on E lesser equal to 0 is transverse. And so the only thing you need to say here is you can perturb now and not change sigma. So after the perturbation, you've only changed somehow your moduli spaces in energy bigger than 0. That's going to give you some numbers here, but I don't care what they are. It's going to keep the same beginning of my map. All right. I've all proofs where that's simple. So, right. So this part here of the regularization machinery allows us to, use this for index 0 to get counts and, define our maps. And it allows us to calculate our map in one specific case. So what's missing is the steps 3 and 4 where we prove relations between the maps. So that's the and before we are able to prove relations, we need to go back a little bit into the general form and say in what sense are there sort of expected relations from expected boundary. So, all right, we don't just have, a Fredholm functor description. We also need to have some kind of gluing functor that explains in what sense the boundary of a moduli space should be given in terms of, boundaries of, in terms of products of other moduli spaces, which I'm all going to fold into one big moduli space right now. Except then there's some kind of fiber product going on. I would like to think of this fiber product only ever as something of a discrete set, like my Morse critical points or my Hamiltonian periodic orbits. If you have a larger fiber product, then you need to generalize this game here. Right, so in the Arnold proof, somehow what you should think, right, there were PSS moduli spaces and SSP moduli spaces and these stretching moduli spaces. And they had many connected components of all the energies and all the indices. And I'm going to throw them all into one gigantic big space, which now isn't compact. Well, it wasn't ever compact because the energy goes off to infinity. But I can cut this at any one energy, and then, you know, in some sense, there's some fiber product that picks out the right boundary terms. And I might have to throw the Morse spaces in also. So how do we explain this in terms of our sections? So the gluing functor should be something on the level of the ambient spaces. Because that's where I can talk about boundary. Right? My underlying Banach manifold has maybe boundary. And I would like that whole boundary to sort of just be diffeomorphic maybe to some fiber product similar to that fiber product of the underlying ambient spaces. And so this is a subset of B. Of course, this whole thing has to go together with the sections. So the restriction of my bundle sits over here. Yeah. So these are all commuting diagrams of categories and functors now. And I should have a similar functor on the level of bundles. So really I only need that functor constructed, because then together with the somehow product of projections that induces this functor on the base. It's just usually we only explain what happens on the base, because once you know what the base is and that your section should be the Debar operator, you know exactly what the fibers ought to be. And in the fibers there's nothing much happening, you just have vector spaces there. Right. And so I could now also draw the sections in here and say that this should all be a commuting diagram, but let me write this slightly different. So I would like to make sure that when I restrict my section on the object level to the boundary, it should be given simply in terms of somehow the products of the two sections on these copies of the moduli spaces. And that then very nicely, with a little more space, explains in what sense this here might be true. It simply says that it's interpreting the boundary of my moduli space as the realization of the zero set intersected with the boundary of the ambient space. So this irregular moduli space by itself has no decent notion of boundary. You know, we're defining what its boundary is by embedding it into a larger space that has a decent notion of boundary. And right, these guys here are the same. So here we have some kind of product section of a product bundle, and that has a fiber product. Sorry, that has well, the fiber, I think, right. I don't like to write fiber product of sections. And I don't have to if this was really a discrete set on which the fiber product happens. And that's really what happens. If that's not a discrete set, then this matching condition here somehow has to be extra equation in this section here. And that also screws up my index identity. So what I'd like to do is to have the index me say that I would like the index of my section on actually B to be the index of these two sections. You know, this is a local identity now, so you need to look at different points. Plus 1. Plus 1 really because this is a section that's only defined over the boundary of B, right? And here this is on all of B. So I could also have said I want the index, I'm expecting the index of sigma on B to be the index of sigma as I restricted it to the boundary plus 1. And on the boundary, this index should be the sum of those two indices, which kind of totally makes sense if it's just a product of Fredholm sections. The problem is that when I say this, I should really go to the true boundary and not on corners. Yeah. So if you went to sort of the subset of corners here, things would get more complicated. Right. And if there needs to be extra condition, if there needs to be extra equation here from a non-trivial fiber product, then that needs to be reflected in this index identity. All right. So that's what I mean by, there's not much gluing in the sense of, pre-gluing and implicit function theorem or Newton iteration going on here. It's sort of just the gluing at infinity, right? You take a pair of trajectories and you declare sort of the pair to be a broken one in the boundary of the new one. But of course, the way that that sits in the boundary, that's somehow the gluing. But that now is part of the structure of this bigger bundle that says how this boundary is attached to the interior. So somehow this gluing data gets sort of pushed into the structure of my section. Okay. Right. In a moment, I'm going to try and say something about how this gluing looks like in the Arnold example. But let me, we'll see that that requires some nice extra properties. Well, not actually of the gluing functor, but of my ambient spaces, of my abstract section. Where do I? Right, I can already see this here. I want to be able to talk about the fiber product, not just in terms of my moduli spaces, but in terms of the bigger ambient spaces. And that fiber product might have something to do with taking limits or evaluating someplace or taking the energy. So there's a whole bunch of maps on my moduli spaces, namely evaluation maps, maybe to the symplectic manifold, or taking limits in the PSS case that sit in the periodic orbits, and also the energy function. That I would all like to extend to my big ambient space. And so I would like these to actually be induced from functors of the same name, that go from B to, these trivial categories which just have this as object spaces and no morphisms. So that's a notion of that actually also exists in the Kuronishi world. I think it's called strongly continuous map, that something that has an extension to this Kuronishi atlas. All right. So with that, How does this look in my Arnold example? So this is the expected boundary behavior here. Right, that was the H is this homotopy, where stretch the sphere and eventually break it into two copies of C. So the breaking here goes into PSS and SSP moduli spaces, and what happens here is that's exactly this case where I have a fiber product over, well, and so now I can be a little bit more anal here. Right, I want to think about fixing the energy here. And that means I can't fix the energy on the two pieces, but I can write this as a fiber product. Where on one I take the limit at plus infinity and the energy, and on the other I take the limit at minus infinity and EI minus the energy. And then if these two agree, then the total sum of the energies is EI. Now, that doesn't look like a discrete set here. Right? So, really, I should think of the possible energies that I have are all discrete, and so I can replace R by a discrete set that in particular includes 0. So it's just more efficient to write it this way. Right. And then the other boundaries that I'm expecting here are right from stretching parameter 0 and from breaking off most trajectories on one or the other end. And here I've left one entry open, so that's fiber products over critical point sets. Right, I'm cheating a little here because that here seems to not be a fiber product or a product of anything. Maybe it's a product with somehow the point. Yeah, very trivial moduli space problem. So I would like to have this mirrored in some boundary strata of my ambient polyfold, right, which I already described very roughly in terms of just taking SFT stretching polyfold and fiber products with the, well, no, not fiber products, right? Now the fiber product with these most moduli spaces goes into my section. And, well, so as a reminder, I think actually you can probably almost uniquely determine polyfolds by saying what their dense subsets are. So there's a dense subset of smooth things here that comes from finite stretching parameter and smooth maps from P1 to P1 times M. And then I can tell you what on this smooth subset my section should be. So this is section on sort of the smooth dense subset. Right? That was going to be, oops, the D bar operator for my graph J that has a parameter R, and then the matching conditions where, and the reason I'm writing this out is that, these have evaluation maps, but clearly I'm going to need an evaluation map at 0 of U hat and also 1 at infinity. So that has something to do with these extensions coming, existing as smooth functors. So that's this. And then as Cartesian product, I know what my boundary strata are. Right? Let me not go into the whole discussion of what corners and boundaries are. So we'll just be a little stoppy here. So this is sort of the entire boundary now, right? It has to come from boundary in one of the three factors, first, second, or third. And then the nice thing is that we know what the boundaries of the Morse moduli spaces are. Namely, I can write, well, if I'm at the boundary, I've broken at least once, so I can write this uniquely as trajectory from with sort of finite end to someplace, and then one unbroken trajectories from someplace to P plus. And that's a fiber product over crit F. And then the neat thing is I've pulled out exactly one of these so that the remaining stuff here is again a version of the H polyfold. And here, this you just have to believe that there is a polyfold that has boundaries on the one hand from stretching parameter 0, and on the other hand from the breaking of my target spaces. And that was the PSS and SSP things, which I called plus and minus. And this is now a fiber product over the periodic orbits and also energy. Well, if I'm careful with energy here, I guess. So if I have energy here, I should have energies here and here. And here they could split in one or the other ways. Right. So if you believe me that there's a polyfold with such boundaries, then you can already see, right, this guy in the middle here is going to give you the polyfold for the I problem. And when you take the product of this on two sides, I can bracket it in different ways and get the PSS and the SSP guy. So that's the upshot here, right? So this guy here goes there. There's the same story in the first line. And the rest gives me back my H polyfold here. From here, I get my I polyfold, because that's the R equal to 0 case. And here I need to bracket in different ways. And so this, together with not the union, but the SFT thing, this is going to be my PSS polyfold. And that together with the minus SFT polyfold is my SSP polyfold. And I've forgotten my energy here. So, hallelujah, right? I now understand the boundary strata of my polyfold. This fits exactly, right, with the expected boundary strata of my moduli space, exactly in this way that I've intersected with the boundary. That is what I think should be the boundary. And so now the abstract statement that I should have in this kind of situation is one, right? So that goes on my wish list for boundary, not empty. Right. I should have the same kind of statement that I had before. I should have multi or sections functors. So that, right, the realizations of the transversely perturbed sections should be, well, weighted branch manifolds of expected dimension, but now with boundary. And the extra condition on the boundary of these things is that it should only run into the boundary if it actually has enough expected dimension to run into that piece of boundary. So if it has expected dimension 0, it should not run into the boundary at all. So that's something about a corner index. But in particular, it should not have boundary that comes from the middle of my ambient space B. So the boundary of this realization should be the realization of its the 0 set intersected with the boundary. And the corner index of these two boundary operators should be the same sort of corner degeneracy. So my polyfold might include 25-fold broken trajectories, which means its corner degeneracy goes up to 25. But if I'm thinking about an index 3 thing here, I want the, this is not even part of the statement, down. Oh boy. Well, so the corner degeneracy here comes from there, right? Which means that if I wanted corner degeneracy 25 here, then this better be at least 25 dimensional. So this is a little hidden here that, you know, when I'm looking at index 1, really the worst thing that can happen is true boundary. So this should be right, one of my statements. And now I need an extra statement that talks about coherence of perturbations. So I should be able to say that if my section on the boundary, so if I just restrict it to the boundary, and let me assume that that also is a polyfold, if I've already fixed a perturbation there, that's transverse over the boundary, which means that nu superscript d is sort of in the set of allowable perturbations for the pair sigma on dB. Then I should be able to perturb and get transversality by asking nu on the boundary to be the given one. And then there's actually one extra condition that has something to do with these products. I should be able to say that the product of two transverse perturbations is transverse. So if sigma 1 plus nu 1 is transverse and sigma 2 plus nu 2 is transverse, then the right, there's the product section and the product perturbation should also be transverse. So meaning if nu1 is in P1, nu2 is in P2, then I would like this to be in the new P for my problem on the boundary. So that's my wish list, and then the exercise that I'm not going to get through is to apply this and, very strictly from the boundary stratification that we had, get to an equation between the boundary of the regularized moduli space of index 1 and the other boundaries of index 0 that we already had. So somehow I should get here to a regularized version of, whoops, what is the, so this should give me a regularized version of the expected boundary stratification now as rigorous statement, and that implies the identity over boundaries. So if you just imagine I'm now taking 0 sets in here, so get the regularized space in here. This is also getting the regularized 0 set in here, regularized in here, everywhere. Regularizing, then I see exactly my identity, right? So sum of one manifold over the boundaries is 0, so left hand side is 0, and then the right hand side is the H composed with differential, differential composed with H, this is I, and this is PSS and SSP. And I've been utterly sloppy about orientations, so the signs go someplace. So, I'll leave that in the notes in full detail. I think it might be. Maybe at some point I'll revisit that when we have even more polyfold notation. But yeah, so this is all rigorous now, modulo making sense of actually what that polyfold is. Floats around here everywhere. So. All right. I am going to declare the Arnold conjecture proven modulo explaining, well, modulo Hofer and Wysotsky and Thin are actually making these SFT polyfolds, and me explaining to you what a polyfold is. Good.